This is precalc chapter 02. We're going to talk about operations with complex numbers. The first thing we should talk about is imaginary unit. What's the imaginary unit? I. Yes, it's I. We did not know about I until we got to Algebra 2. So every number that you guys encountered before then was what we called a real number, and there are such things as imaginary numbers. Imaginary numbers have I. And what does I stand for again? It's not just -1. It's the square root of -1. So hopefully you guys remember that. And the reason why we had to make this up, if you want to say that, is the fact that back in the day, you guys would have done the square root of 25 and said 5. The square root of 50. If you had me before, you would go to the square root dance and look for partners. And so we would do 2 and 25, 5 and 5. The 5s can go to the dance. They become 1 or 5. And the 2 gets left home. So the square root of 50, fully reduced, is 5 times the square root of 2. And then your teacher goes and puts something like this on the board. The square root of -50. And so you're so calculator dependent, you put that on your calculator, and the calculator says error. Some calculators may say no real solution. It's because it's not a real number. It's an imaginary number. Because then you were taught that, wait a minute, square roots are just a fun way of showing rational exponents, fractions. And when you're working with exponents, we have that power of a product rule, and so therefore we can use it to our advantage and say that the square root of 50 is just 50 times -1, yes? So therefore I'm square rooting two numbers multiplied together. And you're like, wait a minute, you can split those up. So I get the square root of 50 times the square root of -1. The square root of -1, we said, was I. And the square root of 50, we just found above, 5 square root 2. Notice that the I is not inside the square root. Sometimes they put it in front of the square root after the 5, so you don't get it mixed up. I like to put it at the end because of complex standard form, which we're going to learn about in a little bit. Okay, quick reintroduction of what I is, how we used it, all of those things in the past. Today we're going to go through the idea of gathering like terms, rationalizing a little bit. So that is I. But here's another question that we can pose, is what's I to the 0 power? It's 1. Anything to the 0 power is. How about I to the first power? It's just I. What about I squared? Well, what does it mean to square something? Multiply to itself. So that's just I times I, which is -1. First of all, if we go back up to our I equals the square root of -1, if I square the left side, I square the right side, and the square root will cancel, leaving me with -1, yeah? Because what you do to one side, you have to do to the other. That's why I squared is equal to -1. Well, then we have to worry about the next one. Okay, so I to the third power equals, well, that's easy. That's I times I, yeah? But could I just kind of group things up a little bit and say, hey, 2 I's make -1. That's -1 times I, which is -I. Interesting. I'm going to get rid of that square root stuff. Give myself a little bit more room here. So you guys can just erase that too if you want. Just kidding, you can't. Don't do that. Okay. I to the 4th power. Well, that'd be I. Well, I got 2 sets of i's, which is -1 times -1, which is 1. Oh. I to the 5th. Or 5 of them. 1, 2 pairs. So -1, -1, and I. All of a sudden now that becomes negative makes a. So it's just I. What do you think I to the 6th power is? Equals -1. I to the 7th power is -I. I to the 8th power. So what's going on here? Keeps repeating. Over and over and over. Not every other. They're not the same every other. Every 4. Every time I have a 4 powers from 0, 0 being the first one, it repeats itself. Hence, that's why I made a whole new column. What I really should have done for the 8th one would be put it on this top row. Could we use this to our advantage, per se, if I asked for I to the 108th power? I think so. How would we do that? Following the pattern. That key concept there is basically the same stuff that we just did. The right-hand side is the ones that have greater than 0. The power is greater than 0. This side has negative exponents. Negative exponents, it doesn't matter. Let's go back to this once. That if I'm here, if I'm at 3, 2, 1, 0, the next one power going backwards would be I to the -1, yeah? Which would start the list over down here at -I. And then I'd go to -1. So it's like I can pick up that list and I can move it backwards or I can move it forwards. It's the same 4 answers are going to be there. And that's what this box is saying, the gray box there. But they're not talking necessarily about the power itself, they're talking about the remainder, the leftovers. The leftovers when you divide by 4. Because there's 2 methods here. They got method 1 and method 2. Method 1 is definitely using a remainder idea. And method 2, it's using the idea of exponents. Method 1 says there's a pattern every 4. If I wanted to know I to the 53rd power, I take the power of 53 and I divide it by 4. That means 4 goes in there 13 whole times with 1 extra. Which means I went through that list 13 complete times. And then I still have 1 step left. And if I take 1 step, where am I? I go 13 times through the list. 13, 13, 13, 13, 13, 13. And I have 1 more. Where am I at? Because I started here, took 4 steps. 1, 2, 3, 4. I'm back to the beginning, right? So 1 more step, remainder 1, I'm at I. A remainder 2, I'd be at -1. A remainder of 3, I'm at -I. If I have a remainder of 0, that's 0, 1. Method 2 says, hey, I can take 53 and I can break it into groups of 4 13 times. 4 times 13 is 52. So I'm using power of a power, right? Power of a power says you would have multiplied there. And then to get that one extra I, that one extra, I have to multiply by the base that's the same. So you add that. So this is 4 times 13 plus 1. Well, what's I to the 4th power?
1.
1. And 1 to the 13th power? 1. 1 times I? I. It's the same thing. It's the same answer. 2 different methods. I don't care which one you use. Use the method that you feel you're more comfortable with. Because both of them use the same pattern. Just like the I to the negative 18. That's negative 18 there. I'm starting to take answers away from you. Isn't that the same thing as taking negative 18 divided by 4? What do I get? How many times is 4 going to 18? Whole. 4 times. So I have a negative 4. What's the leftovers? 2. I'll have a negative 2 out of the 4, right? So watch this. Okay. If I go here, if I start here, and I go back 4 times, 4 complete times, I'm supposed to actually start the list back over down here and work my way backwards. Because these numbers down here would be the negative 1, negative 2, negative 3, right? So therefore, if I have a negative 2 as a remainder, I got to take 2 steps backwards, which is 1, 2. So the answer is negative 1. Boom. Method 2, I got to somehow make that 18, that negative 18, with 4. 4, or sorry, with I to the 4th. I to the 4th to the negative 4 power is power of power, guys. Power of power, you multiply. So what's 4 times negative 4? Negative 16. I got to get to negative 18. So I got to add or subtract 2 more i's, right? 2 more power. But to do that, I have to multiply by I to the negative 2 power. And again, that's walking back twice, and that's 1. Because this is going to be 1 to the negative 4 power, and 1 to any power is 1. And so therefore you end up with I to the negative 2, which is what's a complex number? Someone give me an example of a complex number. Give me a number. Give me a number. 4, 5, 6. I'll tell you they're all complex numbers.
7.4.
Okay, 7.4 as well. Most of the time, we wouldn't say those are complex numbers. We don't think of it as complex numbers because they're real numbers. Right? So if I took this away and left here, what if I did this? 4 plus 5i. That's a complex number, yes. The whole thing, 4 plus 5i, is a complex number. Why? This is a true complex number, as in everybody should recognize, hey, that's a complex number. Because it has what? I. So that means I could also just had 3i, and you guys would be like, hey, I know that's a complex number. We want to standardize things. Because I already said earlier that all the numbers that you guys have ever known, we can write them in complex form. And that form, we want to standardize. And so, that standardized form is A plus B I. complex numbers, if I want to have some kind of definition up there, is a number that is made up of real and complex parts. So then the question is, in the beginning, I said 4, 5, and 6 were all complex numbers. Because 6 is able to be written in complex standard form. 6 plus 0i. There's just no imaginary part. But I can write it in complex standard form. Just like 3i. What's the real part of that? 0. Because there is no real part associated with 3i. So the real part is A, the complex or imaginary part is B. So remember that complex numbers can be written as an ordered pair, as in A, comma, B, and you should be able to graph those, like x, y. So the complex plane. We're not going to do that in today's assignment, but you should know that eventually when we graph polar, rectangular, all of those things, we had i's, we had I hats, j hats all last year. All of this stuff is so interconnected. Okay? So that's what complex numbers are. So let's start using those. Oh, sorry, we got back to here. So an imaginary number is the stuff that has the complex and the real stuff in it. They're all numbers. So I'm not going to give you a definition, but look at this chart. It says complex numbers. Well, the complex numbers have this big world that has all the real numbers in it. Rational, irrational, whole numbers, integers, natural numbers. All of them. But then there's another camp. There's another side. The other side is the imaginary part. The stuff that has eyes in it. And then you get this little subset inside that's contained inside imaginary numbers. And to be pure imaginary, it's kind of like Jake's friends. And that's, yep. And those pure imaginary numbers, can you guess what they would be? Give me an example. Give me an example of a pure imaginary number. 7i. 7i is a purely imaginary number because it has it has I, but it has no real part. If it doesn't have a real part, it's strictly purely imaginary. Okay, let's get into examples here. We only got like 3 examples or so, and then we are going to be done. First one, add 2 complex numbers. Now, the nice thing about I is that you can treat it like a variable. So if I have a variable and I'm adding them together, I gather up like terms. And x plus an x is 2x. It's not x squared. Careful. So an I plus an I is 2i. So when I do these problems, and I only gave you the addition problem, I'm skipping over the subtraction, is that the first thing I need to do is ask myself, do I need the parentheses?
No.
In this case, I do not, because what's in front?
It's a positive.
It's a positive number, a positive 1, in front of each of these sets of parentheses. Now, if there would have been a 5 in front of this parentheses, I would need to distribute that 5. If one of these groups were subtracted, what's really out front? A negative 1, and therefore needs to be distributed. So in this case, I do not need those parentheses, so my first step would be get rid of them. The second step would be gather like terms. So 5 plus a negative 2 is negative 3i plus 4i. Done. We did this last year. You did this in Algebra 2. This is the 0 chapter review. I'm hoping everyone right now is sitting back going, Really? We got it. We'll just move on here. Let's just get into some stuff. But I think it's very important that we go over some of this stuff. Get moving again, okay? Notice that I did some stuff here. I showed my work. That's number one. Number two, I have underlines underneath things I put together. And I put different ones for the different pieces. I can come back to this problem and say, I know I put the 5 and the negative 2 together. You don't have to use my system there, but I would definitely underline, color code, do something so that way you guys can follow some work. It's all about showing me what you know, not just an answer. Next one. A binomial times a binomial. Use the 4-letter F word. Foil. So you need to foil these. So, guess what? This is showing work. That's showing work. Because they're multiplied this time. But guess what I don't want to see? I don't want to see that. What you just said, that's how you show your work, but you don't want to see that? Well, if you had me last year, you know that is the result, but that's not what I want to see right now. I just showed all of my work before I even did anything. When I'm done, you're going to see that. But that's not what I want to see now. I want to see this. 2 times 7? 14. 2 times negative 4i. Negative 3i times 7. And negative 3i times negative 4i. Do you notice that? Hey, wait a minute. Mr. Conjugates, it's the same thing. It is, but I only did one thing at a time. Now, when I made a connection, those are the things I was multiplying. I knew that as soon as I connected those lines, I am not going back to those two. It's a minor detail, but there's so many kids, even at this level, that mess it up. I'm trying to give you guys ways to not mess this up. Don't forget your square. Okay? But now we start to clean things up. We know that I squared should equal negative 1. Okay, so 14 plus negative 12, because it's negative 1 times 12. Oh, it's 2. And I can put all of those together. Negative 8 minus 21.
Negative 29.
There you go. Are we happy? Okay. Again, what form did I put it in? Standard form. You ready to move on?
Yes.
Get ready for this. Okay. Last one. We got to talk about complex conjugates. Now, complex conjugates, guys, are ways that we can handle I. Because, if you remember, when we dealt with square roots and we had fractions, if a square root ended up in the bottom, did we like it? No. So we multiplied by the square root to get rid of it, yeah?
Yeah.
But sometimes it was like 1 plus the square root of 3 on the bottom. And we had to multiply by something to get rid of that. So I has the same thing because I is a square root. It's the square root of negative 1. So we have standard form of a plus bi. That's any complex number. Its conjugate is the exact same thing, but opposite b. The imaginary part is the opposite. It's because that is the sum in difference. You guys remember hearing that? I'm going to sidebar on here. I don't have enough room. I'll erase it after. That's the sum in difference. A plus b times a minus b. Do you guys remember what that equals?
A squared minus AB.
Okay, he's going to work it out. So a times a. a squared, a times negative b, b times a, b, and b times negative b. What happens to the middles? So you're left with a squared minus, what is that called? Difference of squares. It's the difference of squares. The sum and difference when multiplied cancel out the middles, and it squares the ends. Therefore, any square roots or any i's will disappear. That's why we use the conjugate. Okay. So let's work this problem. First of all, you got to divide 5 minus 3i by 1 minus 2i. When's the last time you saw a division sign? Or used it in math class? Last hour in your math class.
That's not math class. It is a math class.
So, we don't like to use that. We like to use a division bar or a division line. So it's 1 minus 2i on the bottom. Bells and whistles are going off saying, hey, I don't like that. There's a I in the basement. In the denominator. So we got to get rid of it. To get rid of it, we multiply that bottom by its, not reciprocal, but by its conjugate. But when I do something to the bottom of fraction, I need to do it to the top of the fraction. So it's 1 plus 2i up there as well. And now you have to use the 4-letter F word twice. So, here we go. 5 times 1. 5 times 2i. Negative 3 times 1. And negative 3i times 2i. And keep going. Now, the reason why I brought that pattern on there is that because eventually you should be able to just use the pattern. For now, I'll still FOIL this out. In the future, we're probably not going to FOIL it. We're going to go straight to the pattern. Let's recognize things. 1 times 1. 1 times 2i. Negative 2i times 1. And negative 2i times 2i. Negative 4i squared. Hey, wait a minute. I squareds become what? So negative 1. Negative 1. Those negatives will cancel out, right? So that negative, so that makes a positive 6. And 6 plus 5 is 11. 10i minus 3i is 7i. So the top becomes 11 plus 7i. That's not too bad. Bottom? Oh, the 2's to 2 i's cancel. Yeah, got to be plus 4. So that becomes 5. We have now just rationalized the denominator. What if it said to rationalize the denominator and put it in standard form? Which means a plus bi form. How do I make that happen? It's a fraction that has a 5 on the bottom. 1 over 5 what? You could multiply it by 1 over 5 to what? Yeah, it's an incomplete thought there. We're getting there. We could do it this one way. CJ?
Just separate 11 over 5 plus 7i over 5.
Yeah. Separate, guys. It's a common denominator. I can separate them to their own fractions. And I'm going to change it just a little bit and make it 7/5 times I. So that way you can see A and you can see B. That is a complex standard form. I was able to take a fraction that looks pretty complicated and create just standard form. Hence, this has fractions in it. It's not always going to have fractions in it. Here's your homework. Point 2, page B8. It looks like a lot, but it's 1 through 54 every 3. E3 every 3. So that means start at 1, skip 2, do another one. AKA add 3. 1, 4, 7, 10. It's the same amount of questions as you guys had to do yesterday.
Why couldn't we do I?
Yes.
Why couldn't we just do I?